All right. So number 4 homework is due tonight. Okay. And there's one, I think one small like typo in problem 4B. You probably get a different number, but it says efficiency would be like 40 something. It meant 40 something percent. Okay, so the percentage sign is missing over there. All right. And then the next two are due like a week from next one a week from now, and then 1 week after that we'll be having a homework number 6 due. And then I have put the exam 2 to be on March the 8th, which is the Monday. Okay, after that midterm break that week. All right. For the classroom disinfection today, it's assigned to Luke and Noah. All right. All right. So today we'll be starting looking at chapter 5 on electrostatics. Okay, so we're starting. So the next a few chapters it's on electrostatics, or basically you can say electricities. We'll be looking at some certain circuits as well. All right. So I think you guys pretty much know some of this knowledge already. So like if I think you experienced electrostatics very much. So if you slide down a slide, particularly in winter, you'll see like there's charge building up on your body. You may see if you have a slightly long hair, you may see your hair stand up like that. Okay, like this. Kitten is playing with something, and then he picks up charge, so then his body attracts these small particles over there. So that's electrostatics. Okay. Charges. So basically, if you have two materials, you are rubbing them against each other, so then they will likely build up charge after that. So that's because, or maybe a couple of slides here. That's because when you are rubbing two materials against each other, so one would have a tendency of losing electrons than the other. All right, so then one will pick up electrons, the other will lose electrons. So then after that, so initially the two should be neutral. So say for example, amber, if it has certain amount of positive charge, it should have the same amount of negative charge. So that should be neutral. And then this cross, if you rub them against each other, so the amber will pick up more electrons. Okay. And then this one will lose a couple electrons. So the amber will be negative charge. This will be positively charged. Okay, so that's basically what happens. So there are basically two types of charge: positive charge and negative charge. Okay, and the assignment of which one carries positive, which one carries negative, actually was very arbitrary. That was originally done. So it was given to the electron to be negative charge. So then anything loses electron will be positively charged. Okay. So two type of charges, like charge, they will repel each other, and then opposite charge, they will attract each other. Okay. The charge, this quantity electric charge, we use Q here. It has SI units of Coulomb, C. Okay, so small q for charge, and then C for the SI unit of it. All right. Now, the source of charges, as I mentioned, is because materials, different material has different tendency of losing electrons. So materials are made of molecules or atoms. So and then also, yeah, they are basically made of atoms because molecules are made of atoms as well. So each atom will have a nucleus and then have electrons surrounding it. So this is a simple model of it, but so you'll see electrons orbiting around it, but in reality, it looks something like this. So electrons has probability of appearing at any location. It's not exactly like circular or like oval orbit like that, but it appears everywhere. Okay, with different possibilities. So when you are rubbing one material against each other, some of the electrons from the atom will um, um, can be moved or can be removed in that sense. So it depends on the tendency. Materials will have tendency of losing electrons, so they will be charged. Okay, so for these materials, all right, they have tendency to lose electrons, so they are positive charged afterwards. Okay, so and then for these ones, they have tendency to pick up electrons, so they will be negative charged. Okay, all right. And any material initially it will be electrically neutral. So then in that process, when you are producing charges, actually charge will conserve because one object will pick up electrons, the other will lose electrons. Okay, so the total should be still equal to 0, electrically neutral. Okay, so that's charge conservation there. Also, you might or might not know, but charge is not continuous, but it's quantized. So that means the amount of charge actually has a small increment of by this amount, 1.60 times 10 to the negative 19 coulomb. That's the amount of charge an electron carries or a proton carries. Okay, so then we use E for the charge, electrons charge. Electron carries negative of this amount of charge. Protons carry positive of this amount of charge. Okay, 1.6 times 10 to the negative 19 coulombs. So then if you have 1 coulomb of charges is equivalent to about 6.25 times 10 to the 18 electrons or protons. Okay. These are also some other fundamental numbers. So for this M sub E, that's the mass of an electron. Okay, so that's a fundamental number. It's a constant of 9.11 times 10 to the negative 31 kilogram. It's a very tiny number. Okay. For protons, this is roughly 100 or 1800 larger than the electron. So it's 1.673 times 10 to the minus 27. A neutron, okay, M sub n is 1.675 times 10 to the negative 27, roughly the same as a proton. Okay, it's slightly heavier, but about the same as a proton. All right. So in a problem, so these numbers might not be given, but you can always look them up because they are constant numbers. They are not changing. Okay. All right. So let's take a look on this example. It says a system of 25 particles, each of which is either an electron or a proton. Okay. So it says it has a net charge of that amount minus 5.456 times 10 to the negative 17 coulombs. So that indicates you have more electrons than protons in this system. It's asking you how many electrons are in the system and then what's the mass of this system. Okay. So basically you can set the two variable to be the number of electrons and then the number of protons. Okay, you can add them up to be 1525. The charges of an electron minus number of electrons plus the charge of a proton times number of protons should be equal to the minus 5.456 times 10 to the negative 17 coulomb. Okay. So I think these are the few numbers you need to use here. So for electron charge, okay, you can say Q sub E or just E. That would be negative 1.6 times 10 to the 9 minus 19. For Q of proton, that should be positive of that, okay? 19. The mass of electron, it's a fundamental number that's not given, but you can look it up. The mass of a proton, it's also a fundamental number, okay? You're looking for number of electrons in part A, so number m sub e. And then at the same time, I think you can solve for the number of protons, right? M sub p. Then you can calculate what's the total mass. Total mass would be equal to the mass of electron times the number of electron plus mass of proton times the number of proton. Okay. You guys can give it a try. We can take a look on the solution in a couple of minutes together. All right. So let's see here. So basically, it tells you that total particles is 5025. So that means number of electrons plus number of protons equal to 1525. Okay. And then it tells us the total charge. So that means QE times NE plus QP times NP equals to minus of 5.456 times 10 to the minus 17 coulombs. Okay, so these two equations, these two are known numbers, so we can put the numbers in there. So minus 1.6 times 10 to the negative 19 times NE plus 1.6 times 10 to the negative 19 times NP, okay, equals to this guy. All right. So you can actually, on this equation, you can actually divide everything both side by 1.6 times 10 to the negative 19, okay? And then also this one times 10 to the negative 19. So you will get rid of this and that, all right? So then minus NE plus NP will be equal to minus of 341 if you do this, okay? So then this equation along with the first equation, you can combine those two to solve for n of E sub E and n sub P, okay? You're looking for n sub E, all right? So you can do, you can call this equation 1, this equation 2, okay? You can do equation 1 plus equation 2. That means the left-hand side equation plus the left-hand side, left-hand side equation 1 plus left-hand side equation 2 equals to the right-hand side equation 1 plus the right-hand side equation 2, okay? So you can do it that way. So then minus positive will cancel out, so be 2 MP on the left-hand side equals to this guy minus that guy. So 1525 minus 341, okay? So you solve for that. Number of protons will be 592. And then you can take this number into either 1 or 2, equation 1 or 2, okay? So you can solve for number of electrons if you take this into this guy. So that means 1525 minus 592, that gives you 933 for the electron, number of electron, okay? So that's part A there. And then for part B, you're looking for the mass of total. So it will be equal to mass of electron times number of electrons. So 9.11 times 10 to the negative 31 kilogram times 933 plus for the electron proton 1.673 times 10 to the negative 27 times the 592. Okay, so that would give you roughly 9.91 times 10 to the minus 25 kilogram. Okay, all right. Okay, any questions? All right. So if not, we can move on here. So the reason that charged particles can pick up small objects is because when you have charged particles approaching the substance, the small objects, the molecules inside the material will reorientate. So because each atom is made of electrons and protons, so electrons and protons inside the atom will rearrange because like charge repel each other, opposite charge attract each other. So then electrons tend to rearrange close to the charged particle here, while the proton will be on the other side. Okay, so then you'll have more attraction force here because this is closer to this guy. Okay, then the repulsive force. Okay, on each of the atoms here, and then that will add up to the attraction force. Okay, so you can see that if you comb your hair with the comb afterward, you will be able to pick up small pieces of paper like that. Or if you approach your comb to a small water stream, it will bend the stream slightly. Okay, so that's because of the electrostatic. All right. Now it happens, it doesn't matter if you have a positive charge or a negative charge, okay? Well, as long as you are approaching light objects, it will be able to polarize the material and then attract it, okay? So it's the same mechanism that the charges will be rearranged inside the material and then there will be positive force attraction there, okay? Okay, so that's pretty much the first section in this chapter. Next section talks about conductors, insulators. So the difference between a conductor and the insulator is for a conductor, there's a few electrons, each atom that can move freely around the body of the material. So then the conduction is through the electrons. Okay, for insulators, all the electrons are bounded to the nucleus, so they are not able to move from one atom to another atom. Okay, so then it's it will not be conducting. So most metals, they are conductors. Okay, and most insulators, they are not metals. They are not metals. Okay. Now, there's another category of material which is not listed here. It's called semiconductor. So it has a tendency to switch from being a conductor and an insulator under different conditions. Okay, so that's called a semiconductor. All right, you can charge an object by having it in contact with a charged particle. So for example, you can charge this device by moving a charge rod over here and then in contact. So then charge will be distributed into this guy. After you remove the charge the rod, this will carry certain charge, okay, because of that in contact. You can also do it by doing induction. So that means you are approaching this charge rod with these two metal spheres. They are in contact. So then charge will be redistributed under the influence of electrostatic interaction over here. Like charge will repel. So positive will distribute around this side and then negative will be on this side. Now after that, you can remove these two, you can separate these two spheres. So then one will be positively charged, the other will be negative charge, okay? And at that point, you can remove this guy. So then both the spheres will be charged, okay? This one will be negative, this will be positive. But because of electrostatic interaction, negative charge now will be on this side and then positive will be on this side, okay? Because you now remove the rod there. Otherwise, you can have a metal sphere over here approaching it with this charge rod. Then charge will be redistributed. Now you can connect this metal to the ground. So then positive charge will be repelled to the ground because of repulsive force by this positive charge rod. Okay. After that, you can cut the wire, grounding wire. So then this one will be negatively charged. Okay. Even you remove this guy, it will be negatively charged. Okay, so that's also charged by induction. All right. So next section talks about what's the strength of the electrostatic interaction between charges. Okay, so we say like charges repel each other, opposite charges attract each other. So in this case, if you have minus minus, they will repel each other. If you have a positive or minus, then they will attract each other. So then force will be in the in both cases, forces are in the opposite direction, but for like charges, they are repelling each other. For the opposite charge, they will be attractive to each other. Okay. Now, the magnitude of the force of the interaction is proportional to the charges Q1 and Q2, the two charges, and then inversely proportional to the separations. Okay, so this can be easily done in a lab. You can observe that, but as the separation increases, the interaction actually weakens. Okay, and so if you put into equation, so the force then will be equal to 1/4 pi times epsilon times the magnitude of or absolute value of Q1, Q2 divided by the separation square, okay, times a unit vector here for the direction. Because force is a vector, you need a magnitude and direction to specify it, okay. The epsilon naught here is equal to 8.85 times 10 to the minus 12. This is a constant number. It's called the permittivity of vacuum of free space, okay. 1/4 pi of epsilon naught is called the Coulomb's constant. 8.99 times 10 to the ninth, okay, in newtons times meters over c square, Coulomb square, okay. You can approximate it as 9 times 10 to the ninth, okay, that's fine, okay. So a lot of times you'll just see like 9 times 10 to the ninth, that would be fine too. All right. So this unit vector for example in here on this chart would be the unit vector of this guy, okay, in that direction, and then on this guy will be in that direction, okay. So it's scenario by scenario, okay. You have to judge it with that, okay. Given like what's the signs of the charges, and then their locations, okay. All right. So the electric forces on two charges, if they are close to each other, they are action and reaction pair forces according to Newton's third law. Okay, so they are the same in magnitude but opposite in directions. Okay, so on different scenarios, they are all true in that case. Okay, so these two like charges, they are so magnitude will be the same but directions are opposite to each other, and then on this case it will be the same too. On this case, it's the same too. Okay, so so remember, magnitude are the same, directions are opposite to each other on the two charges. Okay. All right. Now, in reality, you might have more than two charges that are nearby each other. So then between any two charges, there will be electrostatic forces. Okay, so for example, for charge Q1 here, if it's surrounded by three other charges, then there will be three forces on Q1. Okay, so the force by Q2 on Q1 is the F12. Okay, and then force by Q3 on Q1 is F13. Force of 4 on 1 is F14. Okay. Now remember, forces are vectors. So then for the overall force on Q1 should be the vector additions of those three forces. Okay. So when you are doing vector additions, you do not just simply add their magnitude up. You have to do the components. Okay. You add their components up, and then for the magnitude, you take the square of x component plus square of y component, and then take square root of it. Okay. F is two-dimensional. If it's three-dimensional, you add the z components as well. Okay. All right. So we will take a look on one example here. So this one says you have Q1, Q2, and Q3, three charges. They are Q1 is positive Q, Q2 is negative Q, Q3 is positive Q. They are at the vertices of an equilateral triangle as shown in the figure, the charges have the same magnitude Q but different signs as indicated. Rank the 3 charges in order of increasing magnitude of the electric force they experience. So you want to see which one is having like the magnitude of force, like Q1 or F1, F2, and F3. You want to rank them. If they are ties, you want to indicate. So you can say if F1 is equal to F2, you can say F1 equal to F2. Okay. B, C, D is given the directional angle of the net force experienced by charge 1, 2, and 3. Okay. So you guys can give it a try. We will take a look at the solution in a couple of minutes here together. All right. So let's take a look here. There are 3 charges. You want to know the electric forces on them. So one here is surrounded by these 2 charges. So force on 1 by 3, it should be repulsive. So it's pointing away from charges 3. All right. So that would be F1 by 3 in that direction. Now 2 is negative. So then force by 2 would be attractive force that should be pointing towards 2. Okay. the fact that all three charges are the same magnitude, so then the force should be the same in magnitude. So that means they are about the same length. Okay, so this would be F of 1, 2 on F on 1 by 2. All right. Now the total force on one should be this guy plus that guy. Okay, so that's vector addition. You can do graphically way. So you'll move this guy to that guy, the head of this guy, or the tail of this vector to the head of that vector. So you're moving in that way parallelly over. Okay. So this will be your F1 by 2. Okay. Then the resultant will be from the tail of the first one. This is the first one. This is the second one, pointing to the head of the second one. Okay. So this will be your F1. Okay. So F1 total will be this guy. So this is a equilateral triangle. So that means if this is the same as that one, this is in that direction. Okay, and then this is parallel to that one. So this would be also 60 degree. And these two are the same. So this would be a small equilateral triangle. Okay, so that means this magnitude F1 will be the same as, so for the magnitude wise, you can just write the letter. Okay, the letter here. So F1 will be equal to F1 by 2 equals to F1 by 3. Okay, so those three sides should be the same. Okay, so that's what happens on F1 and its total force. All right, now on 2 here, you'll get a force by charge 1, so that's in that direction, F1 on 1 by 2. Okay, because they are opposite charges. And then the same thing here on 2 by 3 will be in that direction as well. F2 by 3. Then the total force, so these two should be the same length. Okay, now you can do it this way. You can move this guy to this parallelly over here. So something like this, F21. Okay, so then the resultant will be from the tail of the first one to the head of the second one. So it goes in that direction. Okay, this will be F2 total, should be in that direction. All right, and then from the geometry, you will figure that, so these two are the same. All right, you move this guy parallel over. Okay, so then this angle should be still 60 degree, right? Because this two makes an angle of 60. So then this one and this one should be making a 60 degree angle. All right, so this would be 60 degree angle. This would be 120. And then this is the same length as this one. So then each of this angle, these two angles should be 30 degrees. Okay, so 30 degrees there. Oh, let me just put it in this larger view here. If it's 120 degrees, then this is 30, and then 30 here. Okay, 30 here and 30 there. Now you can figure out what's the length of this guy. Okay, this guy. So make a perpendicular line there. This would be the F of 2 by 3 equals to F of 2 by 1. If this is 30 degree, okay, so then this would be, I think a square root 3 divided by 2. Okay, but this will be half of this guy. So this will be square root 3 of 2 of that. And then this is half of it. So multiply by 2. So square root of 3. Okay. So your F2 should be equal to square root of 3 of F23 or square root 3 of F21. Okay. So in that case, or in summary, this guy will be longer than this or that. Okay, so they are all the same. Okay, so you can see F2 will be greater than F1 in that sense. Similarly, you can do for charge 3. Repulsive force by charge 1 goes in that direction on 3 by 1. Attractive force should be pointing to the negative charge of 2 there. So F 2 by 1 there, okay? Now you can do the same vector addition. You move one vector parallelly over here, okay, and then goes there. This would be F3. The total F3 is this guy, okay? So in here, this should be again a small equilateral triangle here. So F3 should be equal to F31 or F21, okay? So without arrow, that means just the magnitude of it, okay? So you can see F1 and F3 should be equal to each other, but F2 should be greater, okay? So if you rank the magnitudes, F1 equals to F3, that should be less than F2, okay? For the angles, then angles for this F1. So F1, you can see this is in the horizontal line. So if this is X direction horizontal, then the angle should be 0, okay? 0 degrees for F1. And then for F2, it's going to be this guy. So 120 over here, 120 over here, plus this is half of the 60, so 30, right? So 120 plus 30 to be 150 degrees on F2, okay? The angle for charge 3 would be this guy. So this is the F3 in this direction, all right? This is 60, this should be also 60, okay? But it's below the x-axis, so it'll be negative of 60 degrees, okay? This is on F3. All right. Questions you guys might have? All right. So if not, we'll take a look on a second example here. So this one is asking you what's the force on the 5.0 microcoulomb charge. There are 4 charges here. All right. It's asking you for the force. Force is a vector, so that means you probably want to give the magnitude and the directional angle, okay, or maybe expressed in the vector form of like x, y, z components, okay. Yeah, I'll give you guys a few minutes to try on this, and then we can take a look at the solution together after that. All right. So let's take a look here. You're looking for the force on this guy. It's surrounded by 3 charges. Okay, so there will be electric force by charge 1. I call this 1, this 2, this 3. So 1 on this guy, which will be repulsive force, so it's pointing away from that charge. There'll be F2. Okay, the electric force by charge 2. It's repulsive. It's going to be in that direction. Now F3 is the attractive force. That means pointing towards the negative charge. So 2 and 3 are in the same direction. Okay, the negative of X direction. So then the total force on this charge at the origin here should be F1 plus F2 plus F3 in vector format. Okay, so that means you're looking for the X direction, F component of the total force, and then Y component of the total force. Okay, now these two are in the negative X direction, so that will be the X component of the total force. You just add those two up. Okay, so then you can put that F total is equal to F1 plus F2 plus F3. Okay, so F total X would be equal to the F2x, right, plus F3x, okay, which will be just the force by 2 on this charge and then 3 by that charge, okay, so it will be, and the direction you can indicate it here, it's negative x direction, so but that's fine. So K, Q, okay, this is will be your Q, you can call it Q0, Q at the origin, Q0. So K, Q0, Q1 over this R square, this is 3 meters square, okay, 3 meters square, and plus K of on this guy, so Q0, Q2, this is also 3 meters square, okay. And then for the direction wise, okay, so we can, let's see. So this should be negative, right? So it should be negative of those two add up, okay? Because that's pointing in the negative direction. Okay, so x of f of sub x should be negative of those. And you can take absolute values as the equation for the Coulomb's law indicated. Okay, so just take the absolute values there. Magnitude and direction. Okay, so minus for K is 8.99 times 10 to the 9 newtons meters square over coulombs. Okay, that's the common factor. You can actually move it out. Okay, so then and then Q0 positive. That's also the common factor. You can put this Q0 out. It's the 5.0 times 10 to the minus 6 coulombs, microcoulombs. Okay, and then the 3.0 is also the common factor, so you can put that out as well. So then it will be basically Q1 plus Q2. Okay, absolute values. So, all right. So this is 3 minus 3. You take absolute value. Oh, actually, I'm sorry. Should be looking for the x direction. This should be 2 here, Q2, and then this should be Q3. Okay. So Q2 here, Q3 there. All right. So these two add up to will be 3 plus 9, so 12 times 10 to the minus 6. Okay, coulombs on this. Okay. So then it will be. It looks like my notes wasn't right, but let me see. So this will cancel out that because this will be 9. This is about 9. Okay, so that can cancel out. So this is 5 times 12 will be 60 times 10 to the minus 6, and then 9, so minus 3. Okay, on that newtons. Okay, so minus of that. That's the x direction. For the y direction, it's only by this force F1. So it's that charge 1 on this force. Okay, so that will be simple, but it's the negative again. K of Q0, Q1 this time, divided by the R square is the 3 meters again. Okay, so minus 8.99 times 10 to the 9th. I'm just going to leave out the units because they are all in SI unit. Okay, so square 5.0 times 10 to the minus 6. Okay, for Q0 and then Q1 is 6.0 times 10 to the minus 6 again in coulombs. Okay, that'll be negative of, so again that will cancel out that, so 30 times 10 to the minus 3 newtons. Okay, That's the y direction. So this is your x component. This is your fx. This is your fy. Okay, y component and x component. So you know those two components, then the magnitude will be square root of the x component square. Okay, so that guy square 60 times 10 to the minus 3 minus square plus 30 minus 30 times 10 to the minus 3 square. Okay, so I think because my x wasn't right, so my number is not right, but you guys can calculate this. Okay, directional angle should be tangent inverse of fy over fx. Okay, you can take those two numbers in. Your calculator will tell you a number, but because your fx is less than 0, right? So remember that. Then you would add 180 degrees to whatever the calculator tells you. Okay, to be your directional angle. Okay, if you express in the magnitude and directional angle, or if you can just say x component is that, y component is that. Okay, so that's also fine too. All right, so I think we'll stop here for today.